In this video, you will learn the fundamental building blocks of quantum field theory, which includes why fields are more fundamental than particles, the challenges in dealing with infinite degrees of freedom, as well as the different strategies which are involved in studying quantum field theory. These strategies include selection of the best books, the essential prerequisites you need to master first, and which books are best suited for beginners and how to use them effectively. By the end of today's video, you will have a clear and a practical roadmap to build a strong foundation in quantum field theory without feeling overwhelmed. My name is Shaunak and you're watching this video on my channel Physics for Students. Well, first let us understand quickly that what is actually quantum field theory. Well, the definition tells something like this, that it is a kind of a theoretical framework that describes how particles and forces emerge as excitations of underlying fields that exist everywhere that you see in space as well as in time. So quantum field theory essentially merges three parts. First of all, that it combines the quantum mechanics, the realm of the very small. Then it takes into account special theory of relativity, which takes into account things which are moving very high at the speed of light almost, and the classical field theory, where it comprises of the realm of continuous fields. Here we see that the particles are not particles, but they are vibrations of fields, or what are called quanta. In simple language, this is the essence of what is called quantum field theory. Now, when we talk of fields, we get first this important concept from particles, how we are moving to fields. In general school books or in other notations, when we talk of particles, we generally find particles, for example, electron, protons and neutrons, which are circling or moving around a center, something similar to our solar system, but it is actually not. The modern physics tells that the particles that moves are basically fields. So an electron is basically nothing more than an excitation in electron field. The protons, well, these are not fundamental particles, so they are excitations of what are called quark fields. They are made up of two up quark and one down quark. Even the photons, they follow the realm of the photon field, and the gluons, the name suggests that something that glues together, that means those which sticks together are excitations of the gluon field. And then we come what is known the elusive thing, that is the Higgs field. So from here what we can say that these are all excitations of the field. Fields you cannot see, you cannot touch, but they are actually present in every point in space. There's something like numbers or tiny arrows which you can see. So you cannot see them, but it is all there. So this is a kind of a basic understanding that these are not anymore particles, but they are excitations of different fields. So from where we can see that when we talk about electrons, positrons or photons, they are really disturbances. So these are nothing but quantum fluctuations. But experimentally, do we see, the fields, etc.? The fact is not that. Neither we see something like the planets moving around the sun or the electrons and protons moving around a nucleus. No. What we see is kind of an abstract picture, something like this. So this image actually represents the probability distribution of an electron, how much probable it is and where it can be present. So you can see there are different colors of the shading. So the shading actually tells that how much the electron is present. What we actually see is mathematically this, that is the square of the probability amplitude, and this picture shows nothing more than an electron, which is how much in a distribution cloud. So it is present in a cloud, and remember, the cloud is not a physical fuzzy ball made of matter. It is a matter, or it is a map of how much probabilities do exist. So this figure which you're seeing right in front of the screen actually shows where the electron is likely to be detected if we try to measure its position. So the denser the areas, the more probable the electrons will be. The lighter the areas, the less probable will be the presence of the electron. So what we see in experiments are neither the quantum fluctuations nor things which are moving around, but just a cloud of distribution, which gives us a kind of a probability where probably the electron would be there. Now, as you understand that when we talk of quantum field theory, people think that these are very difficult things because it has a lot of mathematics and physics to be concerned. So if we talk of the level of difficulty, it is better to understand the subject nevertheless has a reputation of being very difficult, which is perhaps very much well deserved. As you can see that if I consider a simple equation in quantum field theory, it has got a quantum mechanics, it has got space-time, it has got other forces, matter, Higgs together. So it combines quantum mechanics, special relativity, advanced mechanics, field theory all together. So we should understand that yes, quantum field theory is definitely very beautiful, but make no mistake that it is not meant for the people, those who have got a very faint or a light heart. So at the first glance, the diagrams that we see in quantum field theory might seem to be like abstract doodles. So here you can see lines, loops and squiggles scattered on a page. But in reality, they are precisely the visual language. So here you can see that the up quark is moving down and there are particles which are going up and down, a pion, etc. So they are actually pictures of what we call quantum events. The Feynman diagrams, these are just nice illustrations. So physicists working with quantum field theory don't just wrestle with the complex equation, they also describe physical process using a unique languages, which are bubbles, wiggly lines, sharp vertices, each representing real calculable events in the quantum world. So for an untrained eyes, this might seem a little bit difficult, but this is actually the language of the quantum field theory. From here, as we understand the level of difficulty and why it is, we move in another important concept, which is called quantization in quantum field theory. Now, unlike quantum mechanics, first of all, we have something which are called infinite degrees of freedom. So if you see that in quantum mechanics, we typically deal with a finite number of variables. That means variables which are quite limited. A particle has a definite position, a momentum, so work, and we quantize those variables. On the right hand side, you can see this is quantum field theory. Here, instead of finite number of particles, we have infinite degrees of freedom. So more the infinities grows, the life becomes more difficult. So instead of this kind of a psi x, which is a wave function, we start dealing with what are called field operators. So the more we get the infinite degrees of freedom, every point in space needs to be tracked down. Every point needs to be quantized, and hence the mathematics we move from dealing ordinary functions to functionals and operators become a little bit difficult. So the concept of quantization in quantum field theory is a little bit different from that of quantum mechanics. The next thing is that path integrals and operator modes. So when we promote a classical field and their conjugate momenta into operators, they actually satisfy commutation. That means this simple equation in quantum mechanics means that we have a field operator, we have a conjugate momentum operator, and we have a Dirac delta function in 3 spatial dimensions. This is somehow, I would say, analogous to quantum mechanics. Position and momentum of a particle do not commute. Taking quantum field theory, we get on the right hand side an equation like this. I'm not going to explain this equation, neither you need really to know as far as this the scope of today's video is concerned. This Z is called the sum over of all possibilities. Because we are dealing with infinite degrees of freedom, so this actually sums up whatever the possibilities the particle might have. So this d phi actually means integrate over all possible ways the field can behave, and the s phi is basically the Lagrangian, that is the action of the field. That means it tells how the field behaves calculating from the Lagrangian. Don't worry about the mathematics part, it is not important. Just understand the concept and the shift from quantum mechanics to quantum field theory. So here is the diagram which we are already aware. You can see there is the initial position and momentum, there is a final position, and we we can use classical quantum mechanics to calculate. And here comes the problem. When we talk of quantum particle, it can go in this way, it can go in this way, it can take all the possible paths. So that is why this integral sign, that sum over of all possibilities. So this is what is called quantization and the shift in quantum field theory. Now this is the problem. These are the ways and the change in terms of understanding quantum field theory, and from here what we can get are few points which we need to remember. It is not difficult, it is challenging because it comprises classical mechanics, quantum mechanics, special relativity. You need to know electromagnetism as well as the mathematics including calculus, group theory, wave mechanics and so on. You are not dealing with something classical in nature, so consider Lorentz invariance and all kinds of transformation because it is relativistic in nature. The interactions are not particles, they are free fields, so you have to include lot of calculations. There are often renormalizations which are include, that means using with divergent integrals, and the conceptual challenge. It is difficult to visualize because we are no more dealing with small balls of particles, but we are dealing with fields or the fluctuations in the field. So these are the challenges, better to understand, and then we will find out a strategy how to overcome these challenges. So first thing we need to know that what are the prerequisites? What do you really need to know before you step in the world of quantum field theory? Now in general there are mathematical challenges, there are challenges in terms of understanding abstract concepts. In quantum field theory it is different. First of all, you need to have a good mastery of quantum mechanics. Why? Because quantum mechanics I am talking is the non-relativistic quantum mechanics. Then you go into relativistic quantum mechanics, which is QFT. Part 2, most of the students that they ignore is classical mechanics. And what are the areas of classical mechanics which you need to put a special emphasis? On the Lagrangian, on the Legendre transformation, on Hamiltonian formalism and the concept of field theory. Third would be electromagnetism. You should cover Maxwell's equation in terms of the four potentials. And fourth, obviously, Einstein's special theory of relativity, because this is a marriage between all these three or four subjects. So the Lorentz invariance as key symmetry, the particles remains consistent in all inertial frame of reference. All these four things you need to have an understanding. So these are the basic prerequisites in terms of you can take physics or mathematics before we go ahead in learning quantum field theory. Now, as I was telling that most of the students, they ignore, they think that, okay, we have understood Newtonian mechanics or Hamiltonian formalism, we can go ahead with quantum field theory. But I would request that you need to have a special attention in what is called the classical field theory. And in this part of the video, I will tell you what are the best books to understand. The first, which has got a little of criticism because of its dense and rigorous mathematical nature, would be Landau and Lifshitz Course of Theoretical Physics, the Classical Theory of Fields. This is the English edition, as you understand. It is not written in English. So the book by Landau and Lifshitz will be a very good place to start understanding classical field theory. Here you can see I have given a snapshot of the table of contents. So it starts with principle of relativity, then to the relativistic mechanics, then the charge in electromagnetic fields, and so on. It further goes into electromagnetic waves, change of propagation of light, and so on. You can take a make a pause and read out what are the contents which has been covered. It is an amazing book. Quite mathematically dense, but I think this is a very good book to start with, and it concludes to cosmological problems including the redshift, gravitational stability of an isotropic universe, and so on. So if you're really willing to learn and start with the classical field theory, which is a very important base for QFT, you can start with this book. The next book what I would talk about, okay, so these are some of the Amazon reviews which I have put up. No, not required really to look in the reviews because it is a golden book. Everyone knows about Theoretical Physics by Landau and Lifshitz. The second book which I would talk is about our famous and dear Professor Leonard Susskind's book on special relativity and classical field theory. Now, with this name, you can understand that Professor Susskind makes the approach of this book in order to learn QFT, because special relativity with classical field theory gives you an idea that why this book I am mentioning about. So here are a few of the good reviews of Amazon which I have put up. Nevertheless, this is an absolute classic. You can just close your eyes, pick up the book and start learning. I've given a few snapshots about this book. It starts with Lorentz transformation, classical field theory, and goes in classical mechanics. So here you can see the space-time trajectory, the field effects. I've given just few snapshots from the book. So this would be a good place to start learning classical field theory. There are many books available for quantum field theory, but I will be speaking about three important books. Whenever we talk about quantum field theory, obviously the first thing that comes to our mind is Anthony Z's Quantum Field Theory in a Nutshell. Here you can see the cover of the book. Well, when I looked in the cover, I first actually thought, why is this a farmer who is farming a land? Then I thought that it might be that Anthony Z tried to portray that because the farmer is in an untamed land and there are a lot of challenges. Same goes with quantum field theory, because the field in front of you lies with a lot of challenges and and certain incumbents that you need to overcome. So maybe that is a good kind of a justification why this book has got a cover that a farmer is on a field. So this is the Amazon rating, and this is the photograph of the famous Professor Anthony Z. Now the table of contents, here you can put a pause and look in that. So it is around 500 plus pages, very dense and intense book. Starts with the motivation, moves directly into Dirac and the spinner, renormalization, and so on. So you can pause this. I'm not going step by step because otherwise it would be too boring of a talk. Now, when I talk about this book, there are certain strengths, obviously, that it gives you a basic concept of quantization, fields, Feynman diagrams, obviously. It covers Higgs mechanism. I would say, yes, it has got a good development of physical intuition, use a lot of analogies, stories, etc. And it is easy to read compared to other formal textbooks. But however, I have got something to share with you. When I talk of the critical reviews and limitations, I would like to say a few words. First of all, the book is not structured in a very systematic way. Now, if I go back to my video, you will see it starts with the motivation and immediately it comes to Dirac and the spinner. You can see on the part 2, then the spin statistics, and then on chapter 3 directly goes into gauge invariance. Well, I don't consider this to be a very easy and a formal approach to understanding quantum field theory for beginners. This is a little bit quite advanced in nature. And also you see that some chapters jump between these topics, which can confuse students. Path integral formalism is introduced quite early, which should be a little bit later. Not replacement for learning formal methods, and advanced students may find treatment too light on certain precise mathematical techniques. So I won't recommend this for people who are an absolute beginner, because if you're jumping to Dirac spinner in chapter 2, it assumes a huge lot of mathematics. Here you can see I have taken up this chapter 1.8, and I would like to tell you that Professor Z introduces canonical quantization here, but what he does not do is that he doesn't derive the full commutation relation step by step. So that is a problem. Also, the treatment of path integrals is presented in a way that emphasizes how the sum over histories works conceptually, but Anthony Z never tells how the explanation can be done, how the functional integration measure, all those things. So this is not to criticize, but be aware that these type of mathematical maturity and advanced level of mathematics is required by the reader who is going through Anthony Z's book. So in a nutshell, I would say it is best suited for readers with a very solid background in quantum mechanics and special relativity. It is not meant for beginners. Despite this, I would say it is a classic book. It contains clear explanations and a deep insight for exploration in quantum field theory. The next book which I would like to talk about is Student-Friendly Quantum Field Theory by Robert D. Klobb. Now, this book has got this kind of an Amazon rating, and these are few of the snapshots of from Amazon about the book reviews. You can pause and again go through it. Now, student-friendly quantum field theory, you can see it is very dense. You can again pause. I'm not going step by step, but it's a very strategic step-by-step approach in making you understand about QFT. So here you can see the preparation. Part 1 is all about preparing yourself. Then it goes to foundation. Then you see it starts with scalar spin 0 compared to AZ's book, which goes directly to spinors. It starts with Hamiltonian, etc. Then comes the spin 1 fields. Then comes the quantum field interaction and so on. So the table of contents here, again, you can pause, take an understanding of this. The vacuum revisited, renormalization toolkit, regularization, addenda, and so on. So all these things gives the quite a step-by-step approach in understanding QFT by Professor Klauber. So I would say it has been meticulously designed for the derivations, making the complex mathematics easy. In terms of the pedagogical clarity, this is very well structured. I am reading this book. I have already read that. So there are very good charts which are called wholeness charts. The particles, the interaction, everything has been laid out very simply. And it is definitely meant for a student-centric approach. So it has been designed keeping in mind that is meant for student. Sort of what are the common challenges? What are the things that you might feel afraid while reading QFT? These things have been considered. So you will really enjoy while reading this book. Regarding the critical review and limitations, I would say it has got very extensive mathematical detail. The equation starts from one side, left hand side, in almost covers the entire page. So sometimes it seems to be a little bit messy. Also, the length, the treatment of topics are sometimes too lengthy. Okay, the cross section, calculations, etc. And third, I would say the book focuses primarily on canonical quantization. So it does not go deeply on modern theories or covers broad perspective. But overall, I would say this book, I would summarize, is an excellent book. It starts building you the basics. It goes in detailed approach, and readers should be prepared themselves for extensive mathematical content because that is being covered. And overall, it gives you a very solid foundation for quantum field theory. The last book which I would talk about is Quantum Field Theory for the Gifted Amateur, and it is by Professor Tom Lancaster and Stephen J. Bundell. This is the cover of the book, and Amazon rating is 80%. Happy to know that Professor Tom Lancaster is from Durham University, United Kingdom, and I have done quite a number of podcasts from the professors of Durham University and Professor Stephen Bundell from Oxford University, United Kingdom. Now, what can I tell about this book? It is just a Bible. So first of all, let me tell you about the table of contents. Again, intensive, more than 500 pages. Starts with universal as a set of harmonic oscillators. Then it goes to Lagrangian. Why do you need quantum fields? This is very important. It tells you about the limitations of non-relativistic Schrodinger equation and so on. Gauge field theory, propagators and perturbations. Then it goes in the expanding the S-metric Feynman diagram, path integrals, renormalization, taming the infinite renormalization group. All these things have been covered. I'm not going step by step. If you want to know, you can pause the video and take a idea about the table of contents. Finally, the topological field theory, many body problem, superconductors, and the Majorana fermions with suggestions for further reading. Now, this book, I would say, is an excellent book. First of all, again, the conceptual clarity is great because it uses certain things from classical mechanics, which is easy to learn. Harmonic oscillators, which are very important. Second, there are a lot of diagrams, sidebars, which makes the understanding even clear. And the coverage is very good because topics such as Lagrangian, Feynman diagrams, path integrals, these are described in a very concise and clear manner with applications. If I talk of the limitations, okay, before I talk of that, you see here part 1 and part 2. Typically what I liked about this book is that it introduces harmonic oscillators. Why? Now you see that a harmonic oscillator is something very fundamental to classical mechanics. So understanding the concept of quantization from classical mechanics to QFT become easier. So with this model, the learners can develop an intuitive grasp. And also the Lagrangian formalism. This approach actually gives a smoother transition from classical mechanics to QFT. So I feel it is always better that if you are being taught in a way which you already know, and from the known you move in the unknown. So overall, I find that instead of going into path integral formalism and Bhabha scattering, etc., this book takes a different approach using harmonic oscillator and a Lagrangian approach, and the complex concepts are developed step by step. So that makes the learning much more manageable. If I talk of the limitations, really not much. Only that there is limited mathematical depth. That means it is not very rigorous in terms of derivation, and there are no solutions for exercises. That's all. These are the two limitations. Otherwise, this is an absolutely great book to start with. So overall, I can summarize quantum field theory for gifted amateur. This would be an ideal starting point for you, and it goes deep in the subject, intuitive as well as mathematical understanding. So you can pick up the book. I can promise you, if you have learned classical mechanics very well, it would be a cakewalk for you. So here is the time now we can summarize what we have learned. So we have understood what is quantum field theory, why fields are important, that means from particles to fields, the transition. What are the difficulties in understanding QFT? What are the physics and mathematical prerequisites you need to know? The book recommendation which I told regarding classical field theory, Landau and Lifshitz, and the book of Professor Leonard Susskind. And here are the three books which I would recommend one by one if you're picking up. First, pick up quantum field theory for gifted amateur, then go for a rigorous mathematical understanding with student-friendly quantum field theory, and then the third, the very advanced and intuitive understanding, Professor AZ's quantum field theory in a nutshell. So that's all for today's video, giving you a brief idea how to start learning quantum field theory. Thank you for watching this video. Those who have liked, please click on the subscribe button and click on this bell icon so that you get all the notification from Physics for Students. You can follow me on my social media handles, and you can contact me at this email ID. Physics for Students will be soon back with more videos. See you soon, but till then, may the good Lord be with you.